POV driving around London.
Where burial conditions are good. But evidence of our technology, our culture, our intelligence, that would be extraordinarily sparse. A few weird chemical signatures, some unusual mineral distributions. Maybe, if they were very lucky, a few fossilized chicken bones showing evidence of selective breeding, some ceramic fragments that look suspiciously regular, chemical traces of industrial processes in ice cores or rock layers. Would that be enough to prove an ancient civilization existed? Or would it just look like natural variations, unusual but not impossible geological processes, interesting anomalies that don't quite prove anything? That's the fossilization problem, and it's why the Silurian hypothesis is so unsettling. Because if we vanished today, in 100 million years, there would be almost nothing left. Future geologists would have to be incredibly careful, incredibly thorough, and incredibly lucky to detect that we'd ever existed at all. And that means if some other civilization existed 100 million years before us, we'd face exactly the same challenge. We'd be looking for traces so faint, so ambiguous, so easily confused with natural processes that we might miss them entirely, unless we knew exactly what to look for, unless we understood what chemical fingerprints an industrial civilization must leave behind. And that's where our story goes next. So you're looking for evidence of ancient civilizations. You're thinking, okay, buildings decay, metal rusts, even the pyramids won't last forever, but surely something survives, right? Some artifact, some structure, some clear sign that intelligence was here. But what if you're looking for the wrong thing? What if the real evidence isn't in what ancient civilizations built, but in what they changed? Not the structures they left behind, but the chemistry they altered. Not the monuments, but the molecules. Think about what our civilization is doing right now to the planet's chemistry. We're not just building things, we're fundamentally altering the atmospheric composition, the ocean chemistry, the very isotopic ratios that define Earth's chemical baseline. And these changes, they're getting locked into the geological record layer by layer, year by year, creating a signature that could persist for millions of years after every last trace of our cities has crumbled to dust. This is the concept of chemical fingerprints, and it might be the only way to detect a truly ancient industrial civilization. Let's start with the most obvious one, carbon. Not just any carbon, but specifically the ratio between carbon-12 and carbon-13, two isotopes that exist naturally in the environment. Plants preferentially absorb the lighter carbon-12 during photosynthesis, which means fossil fuels, being ancient plant material, are enriched in carbon-12 compared to carbon-13. When we burn coal, oil, and natural gas, we're releasing massive amounts of carbon-12 into the atmosphere. This shifts the global carbon isotope ratio in a way that's completely unprecedented in natural Earth processes. Scientists can measure this shift in ice cores, in tree rings, in sediment layers. The beginning of the Industrial Revolution shows up as a distinct spike in atmospheric carbon-12. It's so dramatic, so clear, that geologists in the distant future would see it instantly, even if they had no idea what caused it. They'd know something weird happened, something that pumped light carbon into the atmosphere at rates that don't match volcanic activity, don't match normal decomposition, don't match anything in the natural carbon cycle. But here's the question that should keep you up at night. Would a similar spike from 100 million years ago still be visible? Would it survive the mixing and recycling of Earth's carbon through oceanic absorption, volcanic outgassing, the slow churning of the rock cycle? Maybe, maybe not. The signature would be diluted, smeared across thousands of years of sediment, but it might still be there, a subtle anomaly waiting for someone to look close enough. Then there's nitrogen. Our civilization has done something to nitrogen chemistry that's arguably even more dramatic than what we've done to carbon. We've learned to fix atmospheric nitrogen, turning inert N2 gas into reactive compounds we can use as fertilizer. The Haber-Bosch process, invented in the early 20th century, has fundamentally altered the global nitrogen cycle. We now fix more nitrogen industrially than all natural processes combined. That's not a small thing. That's a complete transformation of one of the planet's fundamental biogeochemical cycles. And it leaves a signature. Synthetic nitrogen fertilizers have a distinctive isotopic ratio, different from naturally fixed nitrogen. As this synthetic nitrogen washes into rivers, lakes and oceans, it changes the nitrogen isotope ratios in sediments. Researchers have already detected this shift in lake sediments from the past few decades. It's clear, measurable, and entirely artificial. An ancient civilization that developed intensive agriculture would likely have faced the same problem we did. How do you feed billions of people? You need nitrogen fertilizer, and if they solved it the way we did, through industrial nitrogen fixation, they would have left the same kind of isotopic signature in whatever sediments were being deposited during their industrial age. But wait, there's more. Let's talk about something that didn't exist anywhere on Earth until humans invented it. Plastics. Every year we produce over 400 million tons of plastic. Most of it ends up in landfills or the ocean, where it slowly breaks down into smaller and smaller pieces, microplastics, then nanoplastics, eventually just molecules dispersed through the environment. These plastic molecules are remarkably stable. They don't biodegrade easily, they resist chemical breakdown, and they have a unique molecular signature that doesn't exist in nature. Long after every plastic bottle, every shopping bag, every synthetic fabric has broken down into invisible particles, those molecules will still be there, mixed into the sediments, creating a thin but distinct layer of artificial polymers unlike anything in the natural geological record. A geologist millions of years from now might extract sediment cores and analyze them molecularly. Most layers would show the usual organic compounds, natural polymers like lignin and cellulose, typical breakdown products of biological material. But then they'd hit one specific layer, maybe just a few centimeters thick, compressed from thousands of years of deposition, and in that layer they'd find something weird, molecular structures that don't match anything biological. Long-chain hydrocarbons with unusual bonding patterns, the ghost of plastic, the molecular fossil of a civilization that invented synthetic materials. Would this signature survive 100 million years? Honestly, we don't know. Probably not intact. But even heavily degraded, even broken down and partially recycled through geological processes, it would likely leave some anomaly. Some chemical weirdness in that specific layer that doesn't match the layers above or below. Then we get to the really dramatic stuff. Radioactive isotopes. Our civilization has done something that has never happened before in Earth's history. We've created elements that don't exist naturally. When we detonate nuclear weapons or operate nuclear reactors, we produce isotopes like plutonium-239, cesium-137, and strontium-90. These isotopes didn't exist on Earth before 1945. They're entirely artificial, the product of neutron bombardment in reactors and bombs, and they're spreading everywhere. Nuclear weapons testing in the 1950s and 60s scattered these isotopes globally. They're in the atmosphere, in the ocean, in the soil. They're being absorbed by plants and animals, incorporated into bones and shells, locked into sediments as organisms die and sink to the ocean floor. Right now, all over the planet, layers of sediment are being deposited that contain radioactive isotopes that have never existed on Earth before. These isotopes decay over time, but their decay products are distinctive. Plutonium-2-139 has a half-life of 24,000 years, which means detectable amounts would persist for hundreds of thousands of years. Even after it decays completely, the ratio of its decay products, specific uranium and thorium isotopes, would be anomalous. They'd show up in exactly the proportions you'd expect from plutonium decay, not from natural processes. This is a smoking gun that would survive millions of years. Any civilization that developed nuclear technology would leave this signature. The specifics might vary, they might use different reactor designs or weapon types, but the basic principle holds. Split atoms, create artificial isotopes, scatter them globally, leave a permanent mark in the geological record. Scientists have already started calling our current era the Anthropocene, the age of humans, specifically because we're leaving such a dramatic mark on Earth's geology. Future geologists won't have to guess when human civilization existed. They'll see it in the rock record as clearly as we see the asteroid impact that killed the dinosaurs. A thin layer marking a geological instant when everything changed, when atmospheric chemistry shifted, when new isotopes appeared, when artificial molecules showed up in the sediments. But here's where it gets really interesting. If we're leaving such obvious signatures, wouldn't a previous industrial civilization have left similar ones? And if they did, would we recognize them? The answer depends on timing. Our chemical fingerprints will be obvious for thousands of years, probably detectable for millions. But 100 million years? 200 million? The signatures would be degraded, mixed, diluted by the slow churning of geological processes. They might still be there, but you'd have to know exactly what to look for, and exactly where to look for it. You'd need sediment cores from the right locations, places where continuous deposition occurred without disruption. You'd need incredibly precise chemical analysis, looking for subtle anomalies in isotope ratios that might be natural variation or might be something else. You'd need to analyze thousands of samples spanning millions of years, searching for that one thin layer where something weird happened. And even then, even if you found anomalies, how would you know they were artificial? How would you prove they came from industrial activity and not some unknown natural process? A carbon isotope spike could be a massive forest fire. A nitrogen anomaly could be some unusual algal bloom. Even radioactive isotopes could theoretically come from natural nuclear reactors, which have occurred on Earth before in uranium-rich deposits. This is the fundamental problem with looking for chemical fingerprints of ancient civilizations. The signatures exist, they're real, they're measurable, but they're subtle enough, ambiguous enough, that they could be explained away as natural variations. Unless you found multiple independent signatures all occurring in the same layer, all pointing to industrial activity, you'd never be certain. But uncertainty doesn't mean we shouldn't look. It just means we need to be smart about where we look and what we look for. We need to identify the most stable, most distinctive chemical signatures and search for them in the best preserved sediments from Earth's deep past. We need to establish what natural variation looks like, so we can recognize when something exceeds natural bounds. Because here's the thing, if another industrial civilization existed 200 million years ago and lasted just a few thousand years, we might have already seen their chemical fingerprints and dismissed them as anomalies, as measurement errors, as natural variations we don't fully understand. The evidence might be sitting in sediment cores right now, waiting for someone to ask the right questions. Or maybe it's not there. Maybe we're the first. Maybe industrial civilization is so rare, so unlikely, that it's only happened once in Earth's entire history. But we won't know until we look, really look, with the right tools, the right questions, and the willingness to consider possibilities that seem impossible. Because chemistry doesn't lie. Elements and isotopes follow rules that can't be broken. If someone changed Earth's chemistry millions of years ago, some trace of that change still exists, somewhere, in some layer of sediment, waiting. So now we need to ask a more pointed question. If we're looking for evidence of a civilization that existed millions of years before us, what exactly should we be looking for? More importantly, does the geological record contain anything that makes us pause? Anything that doesn't quite fit the standard narrative? The answer is yes. Not proof, understand. Not evidence of ancient alien cities or prehistoric nuclear wars, but anomalies. Strange spikes and dips in the chemical composition of rocks. Events that happened remarkably fast by geological standards. Patterns that look disturbingly familiar when we compare them to what our own civilization is doing to the planet right now. Let's start with the big one, the event that actually inspired the Silurian hypothesis in the first place. 56 million years ago, something extraordinary happened to Earth's climate. We call it the Paleocene-Eocene Thermal Maximum, or PTM, and it's one of the most mysterious events in our planet's recent geological history. Here's what we know. Over a period that might have been as short as 5,000 years, which is nothing in geological time, someone or something released massive amounts of carbon into Earth's atmosphere. We're talking about 3,000 to 7,000 gigatons of carbon. For comparison, humans have released about 400 gigatons since the Industrial Revolution began. Whatever happened during the Petma was an order of magnitude larger. The effects were dramatic. Global temperatures shot up by 5 to 8 degrees Celsius. The oceans warmed. Chemistry of seawater changed so radically that huge numbers of deep-sea organisms went extinct. Acidification spread through marine ecosystems. Weather patterns shifted dramatically. Tropical conditions reached all the way to the Arctic Circle. Sound familiar? It should. Because what happened during the PEM looks remarkably similar to what we're doing to the planet right now. Same basic process. Massive carbon release, rapid warming, ocean acidification, ecosystem disruption. The PEM is basically a preview of our own future if we don't change course. But here's the unsettling part. We don't actually know what caused it. The dominant theory is that massive volcanic activity in the North Atlantic released enormous amounts of carbon dioxide. Alternatively, warming oceans might have destabilized methane hydrogen